In this presentation, we will discuss linear stress-strain relations. Previously, we have tried to throw some light on stresses and strains. We have looked into stresses and strains independently. The theories we presented related to stresses and strains were based on the concept of general continuum. By continuum, we mean a continuous surface. A continuum refers to a continuous substance or a material without any microscopic gaps or voids. The continuum assumption is a simplification used in the structure mechanics. It is based on the idea that at a sufficiently large scale, matter or a body can be treated as if it were infinitely divisible and continuous without considering its atomic or molecular structure. The continuum assumption is particularly useful when dealing with macroscopic phenomena where the effects of individual particles or molecules are averaged out and material properties can be treated as smooth and continuous field. Based on the continuum assumption, we were able to introduce calculus into our calculations. We applied the concepts of stresses and strains on general continuum. The theory of stress was based solely on the concept of force and the associated concept of force per unit area. In the same manner, the theory of strain was related to geometric concepts of infinitesimal line extensions and rotations between two infinitesimal lines. We used equilibrium in the case of stresses to relate body force and surface forces with the stresses. Whereas in the case of strains, we use compatibility equations or compatibility conditions to ensure that the strains are related to the displacements. In the current presentation, we will discuss how the stress at a point in a material will relate to the strain at the point by using constitutive laws, or in other words, material properties. Different materials behave differently when subjected to loads and deformation. Thus, stress-strain relationships depend upon material properties that have to be determined by conducting experiments in lab. It is important to appreciate that only theory doesn't suffice to provide enough information about the material. Lab testing is an important part of working out the constitutive laws. There are general principles for material stress strain relationships. The first principle is deterministic. By deterministic, we mean that if we determine a relation between stress and strain at a certain point in time, that relationship will stay the same at any point in time. In other words, if you give me stress and give me strain in the lab, I will work out the constitutive equation. Today, after 3 days, 5 days, or 10 days, if I determine the stress strain relationship, that will be the same as determined earlier. So that means a deterministic property. In other words, the material doesn't deteriorate or it doesn't kill itself or it become overpowered and change its constitutive equation or material properties with time. This might not be true with a radioactive material whose half-lives are very small. The second principle is local action. By local action, we mean that if we know the strain at a certain point in a body, we can determine the stress using the material constitutive laws at that point without considering strains at other part of the body. So that means a local action. Thus, we can say if you give me a strain at a point, I do not need any other information about the strain at other places to determine the stress at that point. This is called local action principle. The third principle is observer objectivity, which means that material stress strain relationships are independent of frame of reference. In other words, if we test a material in a lab which is in a static condition, the constitutive relations determined would be the same uh, compared to the lab which is in motion or in movement or in a frame of reference whose acceleration is changing. So, in other words, if we determine a stress strain relationship in a lab for a certain material, that stress strain relationship will agree with the test conducted on a high speed train moving at some acceleration. Thus, the movement of frame of reference doesn't have any influence on the material stress strain relationships. The final principle of material constitutive law is that the material will obey laws of thermodynamics. It obeys all the laws of thermodynamics. The most common one are the first and the second laws of thermodynamics. We will discuss the first law of thermodynamics in a minute. In this presentation, we will only discuss elasticity, although there are many different types of material models available. We can have elastic, hyperelastic, hypoelastic, viscoelastic material models. In elasticity, whereas in inelasticity, we can have plastic, viscoplastic, or damage models available. We will only confine our discussion to elasticity. The fundamental tenet of elasticity is that if we have a body, we load it, it will deform. But when we remove the load, it will revert back to its undeformed shape or state. Such sort of bodies are called elastic body, and the stress strain relationship in these bodies do not depend on how and what sequence of operation the material was loaded. It is path independent. So imagine if we have got a body on which four concentrated loads are applied. We call these loads P1, P2, P3, and P4. Now it doesn't matter whether we apply P1 till P4 at a time, or we apply P1 till P4 sequentially starting from P1 and ending at P4, or we apply P4 first and then P3 and then P2 and then P1. So in the case of elasticity, the sequence of the loads doesn't matter. That tells us that in elasticity, we have got path independence. The stress strain relation of a particular material can be derived with the help of first law of thermodynamics. First law of thermodynamics is also called as law of conservation of energy. Thus, according to this law, energy can neither be created nor destroyed. It just changes from one form to another. While describing the laws of thermodynamics, we normally take changes in the energy because the changes in the energy is measurable. The total amount of energy within the system is generally indeterminate. Imagine we have got a system which has got a material inside. That material is subject to some external heat. Heat is the thermal energy flowing into the system, and it is also subject to some external loading, which is shown as W. The first law of thermodynamics states that the work that is performed on a mechanical system by external forces, which is W, plus the heat that flows into the system from the outside equal the increase of the internal energy plus the increase of the kinetic energy. So the internal energy in our definition is actually related to potential energy. And in addition, there can be kinetic energy. Kinetic energy is the energy due to motion. So mathematically, we can write the equation as change in work done plus change in heat supplied is equal to the change in internal energy or change in potential energy plus change in kinetic energy. If we assume an adiabatic process in which the supplied heat is zero, or in other words, no heat is externally supplied, then we are left with the change in work done equal to the internal energy plus kinetic energy. In structures, the kinetic energy of system is very small and that can be omitted. So in the end, we are left with external work done is equal to internal energy. The internal energy over here is actually related to potential energy. So how much energy is actually stored within the particles inside the system is equal to the external work. Now, in order to apply the first law of thermodynamics, we normally consider a loaded member which is in equilibrium. We assume that the deflection of the member is known. We specify the deflection by known displacements as delta U1, delta U2, and delta U3. So delta U1 will be in the E1 direction, delta U2 will be in E2 direction, and delta U3 in E3 direction. We allow each point to undergo infinitesimal increments or variations in displacements, and we indicate that displacement by a small delta, which is shown over here. We can see small delta U1, small delta U2, and small delta U3, which are infinitesimal increments or the so-called variations in the displacement components. We don't consider any variation in the stress component at any point. Therefore, we take the stress component as the full magnitude at a point. Only variations in the displacements are considered. It is important to note that the displacement variations within the body are completely arbitrary, and every particle within the body will occupy a unique position, whether before deformation or after deformation. It is not possible that two particles occupy same point in space. Neither a single particle can occupy more than one position. These conditions will ensure that the material doesn't break, it doesn't tear off, and there is no damage. So we are purely in an elastic domain. Similar to our discussion with stresses, over here we would assume an arbitrary volume of a deformed member enclosed by a surface. We would assume that a member is in static equilibrium following the displacement variations, which is delta x1, delta x2, and delta x3. So our whole body is, is consisting of body forces and surface forces, and both of these forces will be in equilibrium. The surface forces are represented by stress distribution on the surface, whereas the body forces are represented by distribution of body force per unit volume. Body force would have three components: bx1, bx2, and bx3 within the volume V. So coming back to our equation, we have the variation in the external work equal to variation in the internal energy. As per our discussion, the variation in external work can be broken down into variation in the work of the surface forces and the variation in the work of the body forces. Thus, we take a point P of surface S and consider an increment of area ds. The stress vector sigma p acting on the ds has component sigma p1, sigma p2 and sigma p3. So sigma p is made up of three components shown over here: sigma p1, sigma p2 and sigma p3. Each component can be multiplied with the corresponding displacement variation. So sigma p1 is multiplied with the displacement variation in x1 direction. We take sum of the work of this force over the surface ds. Please note that sigma p1 is has got unit of stresses. When it's multiplied with the surface ds or the surface area ds, we get a force. That force is then multiplied with displacement variation delta u1 to get the work of the surface forces in x1 direction. The same thing is done for the work of the surface forces in x2 direction and the work of the surface forces in x3 direction. We know from our previous discussions that sigma p1 is equal to L sigma 1 1 plus m sigma 2 1 plus n sigma 3 1. Thus, based on equilibrium, our component of sigma p is equal to the corresponding component of stresses. Sigma p2 is L sigma 1 2 plus m sigma 2 2 plus n sigma 3 2, and sigma p3 is equal to L sigma 1 3 plus m sigma 2 3 plus n sigma 3 3. Plugging these values, we get an integral expression for the work of the surface forces. The work of the body forces, delta WB, can be written as Bx1 times the displacement variation in x1 direction plus Bx2 times displacement variation in x2 direction and plus Bx3 times displacement variation in x3 direction. Since Bx1, Bx2 and Bx3 are in force per unit volume, they need to be multiplied with dV in order to get the forces, and then correspondingly multiplied with the displacement components to get the work done by body forces. Please note that we are integrating the work done by surface forces over a surface, and we are integrating the work done by body forces over a volume. In order to add these two integrals, we have to make use of so-called divergence theorem. The divergence theorem and the corresponding divergence is explained in the mathematical preliminaries lecture series. Just to remind ourselves, the divergence theorem states that divergence of a vector field integrated over a big chunk of area over a volume is equal to the scalar product of the vector field with unit normal vector on the boundary integrated over a surface area. Thus, this theorem tells us that we can convert a volume integral into a surface integral or a surface integral into a volume integral. We can also say that the flux through a body or through a volume of a sizable body, we can also say that flux through a volume of a sizable body is equal to the flux through the flux through the area through the surface area of the same body. Is this theorem follows the same logic as discussed in fundamental theorem of calculus. This theorem follows the same logic as in fundamental theorem of calculus, according to which if we have a function, a derivative of a function integrated over length x, that would be equal to the value of the same function at b minus value of the function at a. Thus, the function which is integrated over length L is equal to just the value of a function at b minus the value of the function at a. In the same manner, if we have got a flux through a volume of a body, that can be reduced to 1 degree down, which is the flux through the surface area of the body. In order to apply the divergence theorem, we will have to collect all the coefficients of delta U1. In order to apply the divergence theorem, we will have to first of all collect the coefficients of L, M, and N in our delta Ws. Thus, we take L as a common factor and add up all the coefficients of L separately. Then we take coefficients of M and coefficients of N. So once we have these coefficients of the direction cosines arranged, now we can convert that into volume integral by taking divergence, remembering that divergence is equal to partial v by partial x1 plus partial v by partial x2 plus partial v by partial x3, where v is the vector field. So we take partial by partial x1 for this field, then partial by partial x2 for the m component, and partial by partial x3 for the n component. After this, we can add the two integrals. The first coefficient of delta U1 is comprised of three terms, and in this integral, please note that the first coefficient of delta U1 is comprised of three terms. All these terms are getting partially differentiated with respect to x1. So if we apply the multiplication of two variables, please note that every term is consisting of two variables which are dependent on variable x1. Therefore, this is a u times v form of differentiation. So we can take partial derivative with respect to x1 for the first term, and we will get partial derivative of the first term, keeping the second term as it is, and then plus the second term, plus the first term as it is, and partial derivative of the second term. We can find the partial derivative of all these terms corresponding to the three displacement components. After that, we can collect the coefficients of delta U1, and we will get partial sigma 1 by partial x1 plus partial sigma 1 2 by partial x2 plus partial sigma 1 3 by partial x3 plus b1. Thus, so repeating what we said, we can apply the partial differentiation on all the coefficients of delta u's. Every term within the coefficient is dependent on the variable with which we are taking partial differentiation. So that will give us a u times v form. We can apply the partial differentiation on these terms, and in these terms we would get one term in terms of delta u and another term in terms of sigma. The terms which we would get in terms of delta U1 will be then added separately for the whole expression. So terms for delta U1 will come from the first coefficient, terms for delta U1 will come from this second coefficient, from the third coefficient, and from this fourth one, which is also bx1 delta U1. All of them will be added together, and we would get an expression which is in the form partial sigma by partial x, partial sigma 1 by partial x1 plus partial sigma 1 2 by partial x2 plus partial sigma 1 3 by partial x3 plus b1. This expression is equal to 0 as we know from equilibrium. A similar expression can be got corresponding by collecting the coefficients of delta U2 and delta U3. So all the terms corresponding to delta U1, delta U2 and delta U3 will be made 0. Only the terms which are taking partial derivative of the displacement component corresponding to the space will be included. Now, the change of displacement component with respect to an axis of the space is actually the definition of axial strain. Or we can also we can also write partial sigma 1 1 is partial derivative of delta u1 by delta x1. Similarly, partial strain 2 2. Please note that the second remaining term would have a stress component, and please note that the second remaining term would have a stress component times partial differentiation of a displacement with respect to some axes in the space. And this second term is actually our axial strain. So delta epsilon 1 1 will be equal to partial delta u1 by delta by partial x1. Partial epsilon 2 2 is equal to partial delta u2 by partial x2, and similarly delta epsilon 3 3. While deriving our strain equations, we saw that our strain 1 1 is partial u1 by partial x1. Strain 2 2 is partial u2 by partial x2, and strain 3 3 is partial u3 by partial x3. So using the same definition, we can convert this remaining expression, we can bring this remaining expression in terms of strains. So performing all this algebraic activity, we would get the variation in total work done equal to the integral of sigma 1 1 partial epsilon 1 1 plus sigma 2 2 partial epsilon 2 2 plus sigma 3 3 partial epsilon 3 3 plus 2 sigma 1 2 partial sigma 1 2 partial epsilon 1 2 plus 2 sigma 2 3 partial epsilon 2 3 plus 2 sigma 3 1 partial epsilon 3 1. Everything in small bracket and integrated over the volume. Similarly, we can express our internal energy U for volume in terms of internal energy per unit volume. The variation in the internal energy consistent with the variation in work done will be then equal to variation in U naught times dV integrated over volume. And comparing these two equations, we will get our delta U naught equal to everything which is in the small bracket, and that has been written over here and given the name equation B. We can appreciate from this expression that the internal energy is a function of certain variables. We said that the internal energy is actually the potential energy of the internal forces. Therefore, the internal energy is related to the strain components, and we can express the so-called internal energy density in terms of six component of strains: the position, temperature, and also time. This expression, which we call this function, which we call internal energy density function, is dependent on x1, x2, and x3 only if we assume that the material is non-homogeneous, that is, its properties are different at different points. Similarly, the internal energy density is dependent on temperature if we assume temperature dependence of our material. They can be omitted if we consider homogeneous material and assume that and do not consider the temperature dependence. In that case, the internal energy density will be dependent on only six components of the strain tensor. U naught is also called as strain energy density function because it is dependent on strain components. Now, if we assume that the displacements delta displacement, if we assume that the displacements u1, u2, and u3 undergo a small variation delta u1, delta u2, and delta u3, then our strain energy density function will also undergo a small variation, and that variation can be expressed as partial change in the strain energy with respect to epsilon 11 time delta epsilon 11 divided by partial change in u naught corresponding to epsilon 22 times delta epsilon 22, and similarly the partial change in epsilon 33, partial change in epsilon 12, epsilon 13, and epsilon 23. So what we are saying is that if we take variation delta u1, delta u2, and delta u3, then our internal energy density will also show variation, and that variation is equal to variation in that variation is equal to the rate of change of variation in all the variables upon which our strain energy density is dependent. So comparing, we call this variation expression as C. We can compare B and C and we get sigma 11 equal to partial U naught by partial epsilon 11, sigma 22 is partial U naught by partial epsilon 22, and sigma 33 is partial U naught by partial epsilon 33. Similarly, sigma 12 is half of partial U naught by partial epsilon 12. Sigma 13 is half of partial U naught by partial sigma 13. Sig, uh, Sigma 13 is equal to half of partial U naught by partial epsilon 13, and sigma 23 is half of partial U naught by partial epsilon 23. Please note that we have got half appearing over here because of 2's appearing in expression B, and the 2 and the coefficient 2's are appearing in expression A because of our definition of strain, of shear strain, because of our mathematical definition of shear strain as half Uij Uji. So half is coming from the definition of our strain in our as per our previous presentation. From these expressions, we can appreciate that the internal energy is actually equal to the area under the curve. So if we draw a stress strain relation, the internal energy is equal to area under the stress strain curve. According to this expression, we have the strain axis being divided into small parts. Thus, therefore, we can say that area under this curve is our strain energy. Thus, we can also write that sigma times epsilon is equal to the strain energy and the so-called complementary internal energy. So the complementary internal energy plus strain energy will give us stress times strain. In other words, we can also write that C naught is area, C naught is equal to epsilon time d sigma. Or using antiderivative, we can say that epsilon is equal to d by d sigma of C naught. Now, this graphical interpretation is only limited to stress strain curve corresponding to one component. However, we have got more than one components. In our case, every strain is a function of six stress component. So we need to derive a generic expression which consider all these components. From expression D, we can work out the value of C naught by taking the internal energy to the other side. So C naught is equal to minus U naught, and then the product of stress and strain corresponding to all components. And we know from our previous derivation that the stresses and strains, that the six components of stresses and strains are arranged as shown in expression B. So from this, we can write the expression as sigma 11 strain 11, sigma 22 strain 22, sigma 33 strain 33 plus 2 times sigma 12 strain 12 plus 2 times sigma 13 strain 13 plus 2 times sigma 23 strain 23. And we call this expression E. Now we can differentiate this expression with respect to with respect to stress 1, since C naught, which is the complementary internal energy density, is dependent on the stresses. So this expression stays. So this expression is partial C naught by partial sigma 11. The second expression, which is the internal energy density, and that is also a function of sigma 11. So therefore, the second term becomes partial U naught by partial sigma 11. The third term, which is sigma 11 and strain 11 or epsilon 11, that is in U times V form. Both of these variables are dependent on sigma 11. So therefore, we apply the UV differentiation formula. The fourth term has got only epsilon 33. Sorry, the third term has got only epsilon 22 dependent on sigma 11. Sigma 22 is not dependent on sigma 11, and this we clearly mentioned during the start of our lecture when we were discussing local action, in which we said that although the stresses are dependent on all the strain components at the point and the strains are dependent on all the stress component at a point, but a stress or a strain at a point is independent of stress or a strain at other point. So using the concept of local action, we come to the conclusion that sigma 22 is independent of sigma 11, and therefore that becomes zero. So in the other expressions, we have only the epsilons dependent on sigma 1 1 and the stresses are independent of sigma 1 1. So therefore we would get sigma 2 2 partial of epsilon 2 2 by partial of sigma 1 1 plus sigma 3 3 partial of epsilon 3 3 by partial sigma 1 1 plus 2 times sigma 1 2 into partial of epsilon 1 2 partial of sigma 1 1 and similarly the other two expressions. As from our previous expression, we can put the values of sigma 1 1, sigma 2 2 and sigma 3 3 which we derived. Sigma 1 1 is partial of u naught by partial epsilon 1 1, sigma 2 2 is partial u naught by partial of epsilon 2 2 and so on and so forth. So these values can be plugged into this expression and therefore the sigma 1 1, sigma 2 2's, sigma 1 2, 1 3, all of them have been changed and brought in terms of strain energy densities. Now this variation expression of strain energy density was written and given. Now, as we discussed, the variation in internal energy is equal to rate of change of all the variables. If we apply some variation to our displacements delta u1, delta u2 and delta u3, expression C can be partially differentiated with respect to sigma 1 1. And if we take partial differential of this expression, we will get partial u naught by partial sigma 1 1 is equal to partial u naught by partial epsilon 1 1 into partial epsilon 1 1 by partial sigma 1 1. So all these variations can be converted into the partial differentiation with respect to sigma 1 1 and that expression has been written over here. The value of this expression partial u naught by partial sigma 1 1 can be put in expression E and we would get partial c naught by partial sigma 1 1 is equal to so all the terms. So comparing equation E with this expression we realize that starting from the third term till the end are the same as all the terms in this expression. So the third term till the end can be changed with partial u naught by partial sigma 1 1 and that has been done over here. This is partial u naught by partial sigma 1 1 which get cancelled with this negative partial u naught by partial sigma 1 1 and in the end we are left with epsilon 1 1 equal to partial c naught by partial sigma 1 1. We can repeat the same exercise by taking differentiation of the expression of complementary strain energy density with respect to sigma 2 2, sigma 3 3 and other variables and get the ex and get the strains in terms of and get the strain components in terms of complementary strain energy densities.